There is something buried beneath the surface of Mars. For decades, it was completely invisible. But in 2021, a Chinese rover named Zhurong began looking where no rover had ever looked before, beneath the Martian surface. What it found was unexpected. Structures buried 35 meters below the surface. Geometric patterns that shouldn't exist there. And what China uncovered beneath Mars forces us to rethink when water disappeared from the red planet. If you enjoy deep, evidence-based space stories like this, subscribe to the channel and let us know in the comments which country you're watching from. Let's talk about Zhurong itself. The rover landed on Mars on May 14, 2021, making China the second country ever to successfully land a rover on the red planet. The first attempt, that's remarkable. The rover weighs 240 kilograms and is powered entirely by solar panels. It was designed to travel up to 200 meters per Martian day and was equipped with 6 scientific instruments. The landing site was carefully chosen. Utopia Planitia. It's the largest impact basin on Mars, stretching 3,300 kilometers in diameter. That makes it the largest impact basin in the entire solar system. But Utopia Planitia isn't just big, it's old. This region dates back to what's called the late Hesperian period, roughly 3.7 to 3 billion years ago. The basin floor is covered with materials from something called the Vastitas Borealis Formation, or VBF for short. These materials were deposited as a sublimation residue from frozen bodies of water and then modified over billions of years by weathering, wind-driven deposition, and meteorite impacts. The northern lowlands of Mars, where Utopia Planitia sits, have long been hypothesized to have once contained a massive ocean. Scientists have proposed shorelines based on orbital imagery. But the evidence has always been contested because the features are irregular. Shorelines on Earth are level. On Mars, the proposed shorelines vary in elevation by up to 10 kilometers in some places. That's where Zhurong came in. The landing site was selected specifically because it was thought to be one of the best places on Mars to find ground ice at low to mid latitudes. It sits at roughly 25 degrees north of the Martian equator. That's important because most polygonal terrain and periglacial features on Mars are found at latitudes above 30 degrees. This site was unusual. Zhurong landed about 280 kilometers north of one of the proposed ancient shorelines and about 500 meters lower in elevation. If there had been an ocean, this site would have been underwater or near the coast. The goal was to find evidence. The rover carried a ground-penetrating radar system called ROPR, Rover Penetrating Radar. It operates at 2 frequency ranges. The low-frequency channel runs from 15 to 95 megahertz and can penetrate down to 80 meters below the surface. The high-frequency channel runs from 450 to 2,150 megahertz and can resolve structures down to a few centimeters, but only to a depth of about 7 meters. This is important. NASA's Perseverance rover, which landed just a few months before Zhurong, also has ground-penetrating radar. But Perseverance's radar, called RIMFAX, can only penetrate about 10 meters deep. Zhurong's low-frequency radar could go 8 times deeper. Zhurong was originally designed for 90 Martian days, that's about roughly 3 Earth months. But the rover far exceeded expectations. It operated for 1 full Earth year, traveling 1,921 meters across the Martian surface. Then, in May 2022, Zhurong entered hibernation to survive the harsh Martian winter. The rover was expected to wake up in December 2022. It never did. Engineers believe that dust accumulated on the solar panels during the winter storms, preventing the rover from generating enough power to exit its low-power mode. Zhurong has not been heard from since May 2022. But the data it collected during that 1 year of operations is still being analyzed. And it has revealed things that no one expected. The first major discovery came from analyzing the low-frequency radar data. Researchers at the Institute of Geology and Geophysics under the Chinese Academy of Sciences began processing the data using a technique called time frequency analysis. Standard radar analysis looks at vertical layering. That's how you identify different geological layers stacked on top of each other. But the Chinese team decided to look at lateral variations, horizontal changes, differences in the subsurface structure as you move across the landscape. And that's when they found them. Anomalous low-frequency bands, 16 of them. The radar profile showed that the subsurface beneath Zhurong's landing site could be divided into 3 distinct layers. The first layer, from the surface down to about 35 meters, had uniformly distributed energy. This indicated relatively homogeneous material, probably loose sediment mixed with rock fragments. The second layer, from 35 to 65 meters deep, was different. It showed a series of vertical bands with anomalous, low-frequency components. These bands alternated with areas of higher frequency, and they appeared at regular intervals along the rover's entire 1.2-kilometer traverse. The third layer, below 65 meters, was dominated by strong random noise. The radar signal couldn't penetrate clearly beyond this depth. But those vertical bands in the second layer, those were the key. The researchers identified 16 of them. Each band had a dominant frequency of about 45 megahertz, which was roughly 7 megahertz lower than the surrounding background frequency of 52 megahertz. Now, there are several things that can cause low-frequency anomalies in radar data. Surface features like rocks or dunes, or subsurface materials that absorb high-frequency radar waves more effectively than others. The team systematically ruled out each possibility. They confirmed that the low-frequency bands appeared in the original data before any noise removal. They tested different denoising methods and different analysis techniques. Surface features were also ruled out. The rover's path was relatively flat, with elevation changes of less than 0.1 meters over any given 3-meter area. The rover's cameras showed no significant variation in terrain along the path. No large dunes, no major rock formations, nothing that would explain such regular subsurface anomalies. So what were they? The researchers concluded that these vertical bands represented the infilled wedges between columns of buried polygonal terrain. Polygons, geometric shapes carved into the Martian subsurface billions of years ago and then buried under 35 meters of overlying material. Polygonal terrain is common on Mars. It's been observed on the surface in many regions, especially at higher latitudes. But this was the first time polygonal structures had been detected beneath the surface. The average diameter of these buried polygons was about 67 meters. The average width of the wedges between them was about 27 meters, and the height of the wedges, the vertical extent from bottom to top, was about 30 meters. These measurements are important because they tell us how the polygons formed. On Earth and Mars, polygonal terrain can form through several processes: mud cracks from desiccation, volcanic columnar jointing from cooling lava, tectonic fracturing, or thermal contraction cracking from freeze-thaw cycles. The researchers analyzed each possibility. Mud cracks typically have a ratio of crack width to polygon diameter of less than 0.1. The buried polygons had a ratio of 0.4. That ruled out mud cracks. Volcanic columnar jointing would create strong reflections at the boundaries between lava flows and surrounding sediment due to differences in dielectric permittivity. No such reflections were observed, and there was no evidence of volcanic activity in the region. The nearest volcanic vents were over 1,700 kilometers away. Volcanic jointing was ruled out. Tectonic faulting creates long, linear features, but the low-frequency bands appeared intermittently in short segments, suggesting a true polygonal network rather than linear fractures. Faulting was ruled out. That left thermal contraction cracking. This is what happens when ground freezes and contracts, creating cracks. Over time, these cracks can fill with water, ice, or soil material. On Earth, this process creates 3 types of polygons: ice wedge polygons, where ice fills the cracks; composite wedge polygons, where ice sublimates and sediment partially fills the space; and sand wedge polygons where wind-blown sand fills the cracks. The buried polygons detected by Zhurong most likely formed through thermal contraction cracking. But here's the important part. This requires a cold environment, and it might be related to freeze-thaw cycles involving water or ice. The polygons sit at a depth of 35 to 65 meters. Based on crater counting analysis, the materials at this depth formed during the late Hesperian to early Amazonian period. That's roughly 3.7 to 2.9 billion years ago. But here's what's strange. Polygonal terrain on Mars today is mainly found at latitudes above 30 degrees. The Zhurong landing site is at 25 degrees north. That's low to mid-latitude. For polygons to form, they would require a much colder climate than Mars experiences today at that latitude. One explanation is that Mars had a higher obliquity back then. Obliquity is the tilt of a planet's rotational axis. Earth's obliquity is about 23.5 degrees. Mars's obliquity today is about 25 degrees. But Mars's obliquity varies much more dramatically over time than Earth's does, swinging between about 15 and 35 degrees over cycles lasting hundreds of thousands to millions of years. During periods of high obliquity, the Martian poles receive more direct sunlight, causing polar ice to sublimate and redistribute toward the equator. During periods of low obliquity, ice accumulates at the poles. If Mars had a higher obliquity 3 to 4 billion years ago, the Zhurong landing site could have experienced a cold enough climate for polygonal terrain to form through freeze-thaw cycles. The contrast in the radar data above and below 35 meters is striking. Above that depth, the subsurface is relatively uniform. Below it, we see these complex polygonal structures. This suggests a dramatic transformation of aqueous activity or thermal conditions at some point in Mars's history. The researchers believe this marks the cessation of an ancient wet environment. The polygons formed, then the climate changed. The environment dried up or warmed up, and 35 meters of new material was deposited on top, burying the polygonal terrain for billions of years. Now, let's talk about what the high-frequency radar found. While the low-frequency channel revealed structures tens of meters deep, the high-frequency channel provided unprecedented detail of the shallowest layers, down to about 7 meters below the surface. The high-frequency radar on Zhurong is unique. It uses quad polarization. That means it has 4 different modes. HH, where both the transmitting and receiving antennas are horizontally polarized. VV, where both are vertically polarized. HV, where transmission is horizontal but reception is vertical. And VH, where transmission is vertical but reception is horizontal. Why does this matter? Because different polarizations are sensitive to different subsurface features. Co-polarized channels like HH and VV are better at imaging horizontal layers. Cross-polarized channels like HV and VH are better at detecting tilted layers, fractures, and irregular features. The high-frequency data revealed 3 distinct layers in the top 7 meters. The top layer extended from the surface down to an average depth of 0.65 meters. This layer showed weak reflectivity and appeared to be loose, unconsolidated sediment, weathered material mixed with wind-blown sand and small rock fragments. Interestingly, when Zhurong landed, its retro rocket excavated a hole about 0.4 meters deep. Cameras captured images of this hole, showing layered, unconsolidated gravel and sandy sediments. This matched perfectly with what the radar was detecting for the top layer. The middle layer extended from about 0.65 meters down to an average depth of 3.93 meters. This layer showed strong reflectivity, indicating more consolidated material, possibly sedimentary rock, with some degree of cementation. The bottom layer extended from about 3.93 meters down to at least 7 meters, and likely much deeper. This layer showed weaker reflectivity than the middle layer, suggesting different material properties. But the most interesting features weren't the layers themselves. It was what the radar images revealed within those layers: slopes, fractures, buried craters, and thin, centimeter-scale layering. Let's start with the slopes. Throughout the middle and bottom layers, the high-frequency radar detected widespread parallel slopes dipping to the north at angles ranging from 8 to 15 degrees. These slopes weren't random. They appeared consistently over the entire 1.9-kilometer traverse of the rover. On Earth, sloping sedimentary deposits with these characteristics are typical of coastal environments, beaches, shorelines, places where waves and tides carry sediment and deposit it at an angle determined by the energy of the water. The steeper the slope, the higher the wave energy. The slopes detected by Zhurong match the inclination angles of coastal deposits found in 21 different coastal areas on Earth. The angles range from 4 to 26 degrees, with an average around 14 to 15 degrees. The Zhurong data showed slopes averaging 14.5 degrees, with a standard deviation of 2.9 degrees. This is consistent with foreshore deposits. That's the sloping part of a beach between the low tide mark and the high tide mark. Sediments build up in this zone over millions of years, as waves transport material from rivers and distribute it along the shoreline. Then there are the fractures. The radar detected multiple fractures within the middle layer. Some were small and isolated. Others extended from the top of the middle layer down into the bottom layer. One feature, labeled F8 in the research papers, was particularly interesting. It appeared as a concave-up fault dipping southward. At the top of the middle layer, the fault was steep, but as it extended into the bottom layer, it gradually flattened out and became horizontal. This is characteristic of plastic deformation in sedimentary deposits. When sediments rich in salts or clays are subjected to stress, they don't break cleanly like rigid rock. They deform, they bend. The concave-up shape of this fault suggests that the bottom layer contains materials with plastic properties, likely salt-rich or clay-rich deposits. And then there are the buried craters. The radar detected two distinct impact craters buried beneath the surface. The first was located about 1.2 meters deep, between 1,168 and 1,180 meters along the rover's traverse. This crater had a diameter of about 11 meters and a thickness of about 1.2 meters. It was contained entirely within the middle layer and covered by about 0.7 meters of the top layer. The second buried crater was much deeper. It was located in the bottom layer, about 4 meters below the surface. This crater had a similar diameter and a thickness of about 2.1 meters. It was covered by about 4 meters of overlying sediment from the middle and top layers. Interestingly, at one point in the rover's traverse, Zhurong made a U-turn. As it turned around, the radar imaged the same deep crater from 2 different directions. The images were perfectly symmetrical, confirming that the data processing was accurate and that the crater was real. These buried craters are important because they provide evidence of distinct sedimentary periods. The deeper crater formed first. Then it was buried by 4 meters of sediment. Then the shallower crater formed. Then it was buried by less than a meter of sediment. Each burial event required a process that deposited material not just in the craters but across the entire landing area. What process could do that? Flooding, water-driven sedimentation, the characteristics of the sedimentary layers, the presence of slopes, and the preservation of the crater shapes all point to deposition in a shallow aquatic environment. So let's talk about what all of this means. The hypothesis that has emerged from the Zhurong data is that the landing site was once the shoreline of an ancient ocean, or at the very least, a large and long-lived body of water. The evidence comes from multiple independent observations. First, the slopes, the consistent northward dip of sedimentary layers at angles matching terrestrial beaches. Second, the lateral extent. These sloping deposits were detected continuously over a 1.3-kilometer transect, perpendicular to the proposed ancient shoreline. Third, the dielectric permittivity values. The electrical properties of the subsurface materials are consistent with fine to medium-grained sand and silt, typical of coastal sediments. Fourth, The surface observations. Zhurong's cameras and spectrometers detected sedimentary rocks on the surface, with features interpreted as bedding laminations and layered structures typical of water-deposited sediments. Some of these rocks contained hydrated minerals, including gypsum, basanite, and epsomite. These are sulfate minerals that form in the presence of water. And fifth, the high-frequency radar images revealed centimeter-scale thin layering within the middle layer. This type of fine lamination is characteristic of tidal or wave-driven sedimentation. Each thin layer represents a single depositional event, like a tidal cycle or a storm. Now, could these features have been created by something other than an ocean? Researchers considered several alternatives: fluvial deposits from rivers, aeolian deposits from wind-blown sand, volcanic deposits from lava flows. Fluvial deposits can create sloping layers, but they typically show evidence of channel networks and erosional features. The terrain around the Zhurong landing site is relatively flat and lacks typical surface or subsurface fluvial features like valley networks. Fluvial origin was ruled out. Aeolian deposits from sand dunes can also create sloping layers. But dune deposits typically show significant variations in slope angle across the dune profile, and they often exhibit cross-bedding structures where layers intersect at different angles. The Zhurong radar data showed consistent, parallel slopes with no cross-bedding. Aeolian origin was ruled out. Lava flows can create dipping layers as successive flows stack on top of each other. But lava has a much higher dielectric permittivity than sediment, typically around 9 compared to the measured values of 3 to 7 inches the Zhurong data. Additionally, lava flows would create strong reflections at the interfaces between flows due to the sharp contrast in material properties. No such strong reflections were observed. Volcanic origin was ruled out. That leaves coastal deposition as the most plausible explanation. But if there was an ocean here, it wasn't small or short-lived. The continuous detection of sloping deposits over 1.3 kilometers perpendicular to the shoreline indicates a prolonged period of progradation. That's the geological term for when a shoreline builds outward into the water as sediment accumulates. For this to happen, you need 3 things. First, a large enough body of water to generate waves with sufficient energy to transport sediment. Second, a steady supply of sediment from rivers flowing into the water. And third, time. Lots of time. On Earth, beach deposits of the thickness observed in the Zhurong data typically take millions of years to form. Conservative estimates suggest deposition rates of 10 to 40 centimeters per 1,000 years. The 30-meter thick deposits detected at depths of 10 to 35 meters would have required at least 10 to 40 million years to form. This is not consistent with a small, localized body of water or a short-lived melt event. A small lake would not generate waves large enough to create the observed sedimentary structures. And a small lake would not have a distant enough sediment source to supply material for tens of millions of years. The presence of distant rivers is important. The sediment in the foreshore deposits was fine to medium-grained sand. This grain size indicates transport over significant distances. If the sediment source had been nearby, perhaps from local cliff erosion, you would expect coarser grains. But fine sand suggests a primary sediment source sufficiently distant that the rover's radar didn't detect any river channels in the immediate area. So the picture that emerges is this. During the late Hesperian to early Amazonian period, roughly 3.5 to 3 billion years ago, the Zhurong landing site was located on the shoreline of a large ocean or sea. Rivers flowing from the southern highlands transported sediment into the water. Waves and tides distributed this sediment along the beach, creating the sloping foreshore deposits that Zhurong detected. Over tens of millions of years, the shoreline gradually prograded northward as sediment accumulated. The beach built outward into the ocean. This explains why the radar detected multiple layers of sloping deposits at different depths. Each layer represents a successive stage in the shoreline's evolution. Then, at some point, the water disappeared. The climate changed. Mars cooled and dried. The ocean evaporated or froze and sublimated into space. Without water, sedimentation ceased. The beach was exposed to the Martian atmosphere and began to weather. But here's where the story takes an unexpected turn. The buried polygons formed 3 to 4 billion years ago. The ancient beach deposits formed around the same time. For decades, scientists believed that Mars entered a global arid phase about 3 billion years ago. That the surface dried up and has remained dry ever since, except for brief, localized melt events caused by volcanic activity or meteorite impacts. The high-frequency radar data from Zhurong challenges this view, because the layers closest to the surface tell a different story, a story of water activity that persisted much more recently than anyone expected. Let's return to those 3 layers detected in the top 7 meters. The bottom layer, from about 4 meters to at least 7 meters deep, likely extends much deeper. Low-frequency radar data suggests that it connects to a layer that reaches down to about 13 meters. This layer has material properties consistent with the Vastitas borealis formation sediments deposited during the late Hesperian. But the middle layer, from 0.65 to 3.93 meters deep, is different. This layer shows characteristics that indicate formation in a sedimentary environment involving water. The presence of slopes dipping northward at 8 to 15 degrees, the detection of buried craters with well-preserved shapes, the identification of centimeter-scale thin layering interpreted as platystructures or duricrusts. Duricrusts are hardened surface layers that form when minerals precipitate from groundwater or surface water. On Earth, duricrusts form in arid or semi-arid environments where water evaporates and leaves behind mineral crusts. The presence of duricrusts in the middle layer suggests that the Zhurong landing site experienced water activity after the bottom layer was deposited. But when? Crater counting analysis provides the answer. Researchers analyzed the density and size distribution of impact craters on the surface around the landing site. By comparing this to the known impact rate on Mars, they estimated the age of the surface materials. The results were surprising. The materials at the surface and in the top few meters are estimated to be only about 757 million years old. That's less than 1 billion years ago. In Martian geological terms, this is the middle to late Amazonian period. This is supposed to be the dry era of Mars, but the characteristics of the middle layer suggest otherwise. The uniform thickness and continuity of this sedimentary layer, the presence of slopes and buried craters, the detection of thin laminations, all of these point to deposition in a shallow aquatic environment. Now, to be clear, we're not talking about a global ocean in the middle Amazonian. The evidence suggests something much more localized, a shallow lake, or perhaps groundwater rising to the surface during periods of high obliquity. Here's the scenario the researchers propose. During periods of high obliquity, ice from the Martian polar caps sublimates and redistributes toward the equator. At lower latitudes, this ice can accumulate in the subsurface. Then, during subsequent periods, temperature fluctuations can cause this ice to melt, creating temporary flooding at the surface. Alternatively, groundwater could have risen to the surface through cryogenic suction. That's a process where freezing temperatures draw moisture upward from an underground aquifer. As water freezes near the surface, it creates a pressure gradient that pulls more water up from below. This can lead to the formation of ice lenses and, during warmer periods, to surface water. Either way, the key finding is this. The Zhurong landing site experienced sustained aqueous activity as recently as 750 million years ago. Water was present at the surface, or very close to the surface, for an extended period, long enough to deposit a uniform 4-meter thick sedimentary layer across a large area. This is significant for several reasons. First, it extends the timeline of Martian habitability by several hundred million years. If water existed on Mars until 750 million years ago, that's 750 million more years for life to potentially emerge or survive. Second, it suggests that Mars's climate history is more complex than previously thought. The transition from wet to dry wasn't a single, global event 3 billion years ago. It was a gradual process with regional variations. Some areas dried up earlier, others maintained water activity much longer. Third, it has implications for the search for life on Mars. If shallow water environments persisted until the Middle Amazonian, then any microbial life that existed on Mars would have had refuges where it could survive long after the planet's global climate became hostile. These shallow subsurface environments could have served as habitable niches. And fourth, it impacts our understanding of where water is on Mars today. Some of the water that existed 750 million years ago likely still exists, trapped underground as ice or bound within minerals. The Zhurong landing site, and potentially large areas of Utopia Planitia, may harbor significant subsurface water resources. In fact, another recent study using seismic data from NASA's InSight lander estimated that there could be enough liquid water trapped in fractured rocks deep underground to cover the entire surface of Mars to a depth of 1 to 2 kilometers. If even a fraction of that water is accessible, it could support future human exploration and settlement. So, what do we make of all this? Let's step back and look at the bigger picture. Zhurong's discoveries fit into a larger body of evidence that has been accumulating about Mars over the past 2 decades. The Mariner 9 orbiter in the 1970s first revealed valley networks and other features suggesting that water once flowed on Mars. The Viking landers provided the first close-up images of the Martian surface and detected what might be polygonal terrain in the northern lowlands. The Mars Global Surveyor in the late 1990s and early 2000s mapped proposed shorelines in the northern hemisphere and provided high-resolution topographic data. The Mars Odyssey orbiter detected hydrogen signatures consistent with subsurface ice. The Mars Express orbiter used radar to detect massive ice deposits beneath the surface in several regions. The Spirit and Opportunity rovers found mineral evidence of past water, including hydrated sulfates and clays. Opportunity, in particular, spent years exploring sedimentary rocks in Meridiani Planum that formed in an ancient aqueous environment. The Curiosity rover found mudstone deposits in Gale Crater and detected organic molecules, both indicators of a past environment that could have supported life. It also imaged mud cracks on the surface, evidence of repeated wet-dry cycles during Mars's warmer past. The Perseverance rover is currently exploring a river delta in Jezero Crater, collecting rock samples that will eventually be returned to Earth for detailed analysis. Its ground-penetrating radar has detected sloping layers that could be sedimentary or volcanic in origin. The jury is still out. And now Zhurong has added direct subsurface evidence of ancient beaches, buried polygonal terrain, and recent water activity at low latitudes. The pieces of the puzzle are coming together, but many questions remain. The biggest is this: when exactly did Mars have a stable ocean, and how long did it last? The evidence suggests that the northern lowlands were covered by water during the late Noachian to early Hesperian period, roughly 4 to 3.5 billion years ago. But the exact timing and duration are still debated. Some researchers argue that the ocean was episodic. It filled and drained multiple times as Mars's obliquity varied and as volcanic activity released greenhouse gases that temporarily warmed the climate. Others argue that the ocean was more stable, lasting for hundreds of millions of years before gradually drying up as Mars lost its atmosphere. Another question is where all the water went. The polar ice caps contain some water, but not nearly enough to account for the volume suggested by the geological evidence. Some water escaped to space as Mars's atmosphere was stripped away by solar wind, but recent studies, including the InSight seismic data, suggest that large amounts of water remain trapped underground. A third question is whether life ever existed on Mars. The environments detected by Zhurong and other missions, shorelines, shallow lakes, wet-dry cycles, are exactly the types of environments where life is thought to have originated on Earth. If life emerged on Mars during the late Noachian or Hesperian period, It would have had hundreds of millions of years to evolve before the planet's surface became inhospitable. And if life did emerge, could it have survived underground as the surface dried up? Microbial life on Earth is incredibly resilient. It exists in deep subsurface environments, in permanently frozen permafrost, in hyper-arid deserts. If Mars had life, it's plausible that some of it found ways to persist in underground refuges. The discovery of recent water activity by Zhurong suggests that these underground environments might have remained habitable far longer than we thought. Not billions of years ago, but hundreds of millions of years ago. In geological terms, that's recent. There's a bittersweet element to this story. Zhurong's discoveries are groundbreaking, but the rover itself is silent. As mentioned earlier, Zhurong entered hibernation in May 2022 to survive the Martian winter. The plan was for the rover to autonomously wake up when solar power levels increased in late December 2022, but that didn't happen. Images from NASA's Mars Reconnaissance Orbiter show that Zhurong has not moved from its position since it entered hibernation. The rover is still there, sitting on the Martian surface, but it's not responding to commands. Engineers believe the problem is dust. Mars is a dusty planet. Dust storms can last for months and cover entire regions. Even when there's no global dust storm, local dust devils and wind-driven dust constantly coat surfaces. Zhurong's solar panels were likely covered by a layer of dust during the winter. Without enough sunlight reaching the panels, the rover couldn't generate sufficient power to wake up. It's stuck in a low-power safe mode, unable to communicate with Earth. This is the same fate that befell NASA's Opportunity rover in 2018. Opportunity operated on Mars for nearly 15 years, far exceeding its expected lifetime. But when a global dust storm coated its solar panels, the rover lost power and never recovered. It's a reminder of the challenges of exploring Mars. The planet is hostile: dust, extreme cold, radiation, thin atmosphere. Equipment fails, missions end. But the data they collect lives on. Zhurong traveled 1,921 meters during its 1 year of operations. That's just under 2 kilometers. But in that short distance, it collected data that has reshaped our understanding of Martian history. The buried polygons, the ancient beaches, the evidence of recent water activity. None of this would have been known without Zhurong, and the data is still being analyzed. The research papers published so far represent just the first wave of findings. As scientists continue to process the high-frequency radar images, the spectroscopic data, and the camera images, more discoveries are likely to emerge. China has announced plans for a Mars sample return mission, potentially launching in 2028 or 2030. The target site has not been officially confirmed, but Utopia Planitia is a strong candidate. If samples from the Zhurong landing site could be returned to Earth, they could be analyzed in laboratories with far greater precision than any rover instrument can achieve. Age dating of the sedimentary rocks, detailed mineralogical analysis, searches for organic molecules or biosignatures. All of this would be possible with returned samples. In the meantime, other missions are continuing to explore Mars. Perseverance is collecting samples in Jezero crater. The European Space Agency's ExoMars rover, Rosalind Franklin, is scheduled to launch in the late 2020s. It will carry ground-penetrating radar and a 2-meter drill capable of extracting subsurface samples. NASA's Mars Reconnaissance Orbiter and ESA's Mars Express continue to monitor the planet from orbit. And new missions are being planned by space agencies in the United States, Europe, China, India, and the United Arab Emirates. Each mission adds another piece to the puzzle, and the picture that's emerging is of a Mars that was once far more dynamic and habitable than the frozen desert we see today. But there's a paradox at the heart of all this. The evidence for water on ancient Mars is overwhelming. Valley networks, lake beds, river deltas, shorelines, sedimentary rocks formed in water, hydrated minerals. The list goes on. But here's the problem. Mars is a small planet. It has only about 11% of Earth's mass. That means it has weaker gravity, and weaker gravity makes it harder to hold onto an atmosphere. Without a thick atmosphere, Mars can't retain heat. The average surface temperature today is -60 degrees Celsius. That's well below the freezing point of water. And without atmospheric pressure, liquid water can't exist on the surface. It either freezes or sublimates directly into vapor. So how did Mars ever have stable surface water? That's the climate paradox. And it's one of the biggest unsolved questions in planetary science. The most common explanation is that early Mars had a much thicker atmosphere, rich in carbon dioxide and other greenhouse gases. These gases would have trapped heat from the sun, creating a greenhouse effect that warmed the planet enough for liquid water to exist. But here's the catch. Climate models have trouble producing a warm, early Mars, even with a thick carbon dioxide atmosphere. The problem is that the sun was fainter 4 billion years ago than it is today, about 25 to 30% less luminous. That's called the faint young sun paradox. To compensate for the faint young sun and warm Mars enough for liquid water, you'd need atmospheric pressures much higher than what geological evidence suggests. Or you'd need additional greenhouse gases like methane or hydrogen. But where would those come from? Volcanic activity is one possibility. Mars had extensive volcanism in its early history. Volcanoes release carbon dioxide, sulfur dioxide, water vapor, and other gases. If volcanic activity was intense enough, it could have thickened the atmosphere and warmed the planet episodically. Another possibility is meteorite impacts. Large impacts release enormous amounts of energy. They vaporize rock and ice, creating temporary thick atmospheres that could trap heat for thousands or even millions of years after the impact. Early Mars was heavily bombarded by meteorites, so this could explain episodic warm periods. A third possibility is that Mars's obliquity varied more dramatically in the past than it does today. When obliquity is high, polar ice sublimates and redistributes to lower latitudes. This increases atmospheric pressure and could trigger greenhouse warming through changes in the distribution of ice and dust. But none of these explanations fully solve the paradox. The fact is, we don't yet understand how Mars had stable liquid water on its surface for potentially hundreds of millions of years. It's a puzzle. And the discoveries by Zhurong make the puzzle even more complex. Because now we have evidence that water activity persisted not just in the Noachian or Hesperian, but into the Middle Amazonian. That's much more recent than models predict. One possible explanation is that the water detected in the Middle Amazonian layers wasn't surface water in the traditional sense. It might have been groundwater rising to the surface temporarily during periods of high obliquity, or it might have been snowfall that briefly melted during warmer periods. Another explanation is that the Zhurong landing site had unique local conditions that allowed water to persist longer than elsewhere on Mars. Perhaps there was a local heat source, like geothermal activity from subsurface magma, or perhaps the topography created a microclimate that trapped moisture. But these are speculations. The truth is, we don't know, and that's okay. That's how science works. We gather data, we form hypotheses, we test them, and when the data doesn't fit our models, we revise our understanding. What's clear is that Mars's climate history is more complex than a simple transition from wet to dry. There were multiple phases, regional variations, episodic events. The story is messy, but it's also fascinating. Let's talk about life, because ultimately, that's what drives much of the interest in Mars. Not just water, not just climate, but the question of whether life ever existed there, and if it did, whether any trace of it remains. Life as we know it requires three things: liquid water, organic molecules, and an energy source. Mars had all three during the Noachian and Hesperian periods. It had liquid water on the surface. It had organic molecules delivered by meteorites and produced by volcanic activity and atmospheric chemistry. And it had energy from sunlight, geothermal activity, and chemical reactions. The environments detected by Zhurong are particularly interesting from an astrobiological perspective. Shorelines, shallow water, wet-dry cycles. These are the types of environments where life is thought to have originated on Earth. On Earth, the earliest evidence of life dates back to about 3.8 to 3.5 billion years ago. Fossilized microbial mats, stromatolites, carbon isotopes consistent with biological processes. All of this has been found in ancient rocks that formed in shallow marine environments. The shorelines and shallow lakes on Mars during the same time period would have provided similar conditions. Cycles of wetting and drying can concentrate organic molecules, facilitating the chemical reactions that lead to the formation of complex molecules like RNA and proteins. Tidal zones provide mixing of nutrients. Sunlight provides energy. If life emerged on Earth 3.8 billion years ago in these types of environments, it's entirely plausible that life could have emerged on Mars during the same era under similar conditions. But here's the question. If life did emerge on Mars, would we be able to detect it? That depends on what kind of biosignatures we're looking for. Fossils are one possibility. On Earth, microbial fossils have been preserved in rocks for billions of years. If Martian life existed, it might have left similar fossils. But finding fossils is hard. They're small, they're rare, and after billions of years of geological activity, most would have been destroyed. You'd need to drill into ancient rocks and examine them with microscopes. That's beyond the capabilities of current rovers. Another type of biosignature is organic molecules. Life produces organic molecules with specific structures and isotopic ratios that are difficult to explain through non-biological processes. Perseverance has detected organic molecules in Zhurong crater, but organic molecules can also form abiotically through non-biological chemistry. Distinguishing biological from non-biological organics is challenging. A third type of biosignature is mineral deposits. Life often mediates mineral formation. On Earth, certain types of iron oxides, sulfates, and carbonates form through biological processes. If similar minerals are found on Mars with textures or compositions that suggest biological involvement, that would be compelling evidence. And a fourth type of biosignature is patterns, seasonal cycles in atmospheric methane, variations in mineral deposits that correlate with water availability, structural features like layered mats or branching filaments. These patterns can suggest biology, though they're rarely definitive on their own. The challenge is that Mars has been geologically active for billions of years. Rocks get buried, heated, fractured, and eroded. Organics get destroyed by radiation and oxidation. Biosignatures fade. The older the rocks, the harder it is to find preserved evidence of life. That's why the recent water activity detected by Zhurong is so intriguing. If water existed at the Zhurong landing site until 750 million years ago, any life that existed there would be much more recent than life from the Noachian period. The biosignatures would be better preserved. The rocks would be less altered. Of course, this assumes that life still existed on Mars 750 million years ago. That's not a given. If life only emerged during the Noachian and then went extinct as the climate dried, then even the recent rocks at the Zhurong landing site wouldn't contain biosignatures. But if life found a way to persist underground, in aquifers or ice layers, then the recent aqueous activity at the surface could have brought microbial life, or traces of it, to the near-surface layers. Those layers are within reach of current drill technology. This is why sample return missions are so important. To definitively detect biosignatures, you need the kind of sophisticated analysis that can only be done in Earth-based laboratories. Mass spectrometers, electron microscopes, isotope ratio measurements, DNA sequences. On the off chance that Martian life uses something like DNA, Perseverance is currently collecting samples that will eventually be returned to Earth by a future mission. If samples from the Zhurong landing site could also be returned, they would provide a second, independent dataset from a completely different region of Mars. That would be invaluable. So what have we learned? China's Zhurong rover operated on Mars for just 1 year. It traveled less than 2 kilometers. Then it fell silent, likely never to wake again. But in that short time, it collected data that has fundamentally changed our understanding of Mars. It detected buried polygonal terrain 35 meters underground, evidence of freeze-thaw cycles during the late Hesperian. It imaged ancient beach deposits with slopes and layering characteristic of coastal environments. And it found evidence of water activity as recent as 750 million years ago. Each of these discoveries challenges previous assumptions. Polygonal terrain at low latitudes suggests Mars had a much higher obliquity in the past. Ancient shorelines detected in the subsurface provide strong support for the ocean hypothesis. And recent water activity extends the timeline of Martian habitability by hundreds of millions of years. But for every question answered, new ones emerge. How long did the ancient ocean last? Where did all the water go? Why do climate models struggle to explain a warm early Mars? And most importantly, did life ever exist on Mars? We don't have answers yet, but we're getting closer. Each mission adds another piece to the puzzle. Zhurong detected ancient beaches. Perseverance is exploring a river delta. Future missions will drill deeper, analyze samples, and search for biosignatures. The story of Mars is a story of transformation. A warm, wet planet that became cold and dry. A world that might have harbored life that became inhospitable. But beneath the surface, hidden under tens of meters of dust and sediment, the evidence remains, waiting to be discovered. Zhurong found some of that evidence, and even though the rover is silent now, its legacy lives on in the data, in the papers, in the discoveries, in the questions it raised and the paths it opened for future exploration. Mars was once a world of oceans and rivers, of beaches and shorelines, of freeze-thaw cycles and shallow lakes, and perhaps, just perhaps, of life. What China found buried under Mars isn't just geological data, it's a window into a lost world, a planet that was, in some ways, not so different from Earth. And understanding that world helps us understand our own, how planets evolve, how climates change, how life emerges and adapts, and survives, or doesn't. For now, all we can do is keep looking, keep analyzing, keep exploring. The answers are there, buried beneath the surface, and with each passing year, we get a little bit closer to uncovering them.